Welcome back to another video. We introduced set systems, semi-rings, rings, and sigma algebras. Today we are going to define even more set systems, which are so-called Dynkin systems and compact systems. Dynkin systems we will need in order to show that something which we might have in some proof or a statement or so is in fact a sigma algebra. Because the main theorem on Dynkin systems is that an intersection stable Dynkin system is in fact a sigma algebra. I will come to the definition in a minute. And compact systems, which we will also need later for measures. And compact systems, so the most basic one is the set of all compact sets of space. And yeah, how this is defined, you might already know when you took a course in topology or maybe some more extended course in calculus. Okay, let's get started. Let us start with the Dynkin systems, and we then also come to compact systems where we need some more topology. To recall, we have semi-rings, we have rings, we have sigma fields, also called sigma algebras. We saw that for semi-rings, for example, the set of intervals, they are easy in the sense I can easily describe them. We have rings generated from semi-rings, for example. They're also pretty easy to describe because, as we saw, we just need to take all disjoint unions of members of the semi-ring in order to get the generated ring. For the sigma field, it's more complicated. We don't really have a good example of this yet. In this video, we will introduce Dynkin systems. Why are we doing this? We are doing this mainly because of this result here, which says if I have a Dynkin system, that's something which is a bit easier than a sigma algebra, and if I know it's intersection stable, then I already know it's a sigma algebra. So in order to see that something is a sigma algebra, which is something which I eventually have to do, I need to show, okay, it's intersection stable, that's usually easy, and it's a Dynkin system, which is a bit easier to check than the properties of sigma algebra. So what is a Dynkin system? Why is that easier than a full sigma algebra? Okay, the full set has to be in it. It's set difference stable only for subsets. Okay, that's a bit more special. So B without A is in the Dynkin system only for A part of B, which is maybe not a huge restriction. And also this sigma union stability that also holds for the Dynkin system, but only in the sense that if A1, subset of A2, subset of A3, and so on, then the union, the countable union, is again in the Dynkin system. So there are some restrictions which are maybe sometimes easier. Yeah, what can we say? A sigma algebra is a Dynkin system. Yes, of course, because for sigma algebras, we know, okay, omega is in it. It's set difference stable, not only for subsets, but for all sets. And the third property also holds for all choices of AN, not only for those increasing sequences here. So that's easy. A Dynkin system is complement stable. That's important because sigma algebras are complement stable. So why is the Dynkin system complement stable? Because every set is a subset of omega, and omega without A, so the B here is the omega without A, that's again in the Dynkin system, so a complement is in the Dynkin system. So we have this, and we now come to here theorem 1.13. Here I said intersection stable Dynkin systems are sigma algebras. It's a bit more general here, I have a Dynkin system D, and I have any intersection stable system C here, then sigma of C, so the sigma algebra generated by C, is part of D. And of course, what I do not have to mention is that this here is part of sigma of D. So if C equals D, when you apply this here, if C equals D, then sigma of D as a subset of D, and D is a subset of sigma of D, then D equals sigma of D, which means D is a sigma algebra, because sigma of D is a sigma algebra. So in this sense, this assertion here is more general than this here. So let's prove this here. I wrote it down because the proof is a bit complex, so I can see the structure of the proof better here. First of all, let me correct something because that doesn't really make sense here. So we have sigma algebras generated by some set C, that was sigma of C. Here we have Dynkin systems generated by C. So lambda of C is the intersection of all Dynkin systems which are bigger than C. And of course, that's a superset of C. I have to show that lambda of C is a sigma algebra. Because if lambda of C is a sigma algebra, then, okay, C is subset of lambda of C, that's clear. And sigma is monotone, so sigma of C is subset of sigma of lambda of C. But if lambda of C is a sigma algebra, then sigma of a sigma algebra is the sigma algebra itself, lambda of C. And lambda of C is a subset of D, because D is a Dynkin system larger than C, and therefore also larger than lambda of C, because the lambda of C is an intersection of all Dynkin systems which are larger. So lambda of C, in this intersection, you also have D itself. So lambda of C is subset of D. So when we show that lambda of C is a sigma algebra, we have that sigma of C is subset of D, which is the claim here. So why is lambda of C a sigma algebra? What do we have to prove? I say it suffices to prove that lambda of C is intersection stable. That's all we have to prove, because then, first of all, if it's intersection stable, it's also union stable, because I can write the union like this here. And since all Dynkin systems here are complement stable, what we saw here, A complement and B complement are in lambda of C. If A and B are in lambda of C and complement stable, so lambda of C is union stable. And if we have A1, A2, and so on in lambda of C, then we can write that the infinite union, well, I just smuggle this in here, union of 1 to n, AI, so that doesn't change the complete union. But I write it like this here because this here in n is an increasing sequence of sets. And for this, I know that they are again in the Dynkin system. So that's in lambda of C also. So all what remains to do is that to see that lambda of C is intersection stable. And that has two steps here. Fix B in C. So B is a fixed set now. So this B here is fixed. And I take the subset of all sets A such that A intersection of A and B is in lambda of C. And I say here, that's a superset of C, because if A is in C and B is in C, then I have A intersect B, and I know that C is intersection stable, so this here is then also in C, and therefore it's also in lambda of C. The claim is that DB, that's a Dynkin system. Let's see. DB is a Dynkin system. And let me write down some things on this here. Let's just complete the proof here. I claim that DB is a Dynkin system. Let's just assume we have shown that DB is a Dynkin system. What would follow then? So DB is a Dynkin system which is bigger than C, therefore it's also bigger than lambda of C. So lambda of C is a subset of DB. So lambda of C is a subset of DB. Now let's pick A in lambda of C. And similar to what we have done here, pick another set. So A is fixed now. A is a fixed member of lambda of C. And we are looking at the intersection of A and B such that this is in lambda of C. So if A is in lambda of C, so first of all, this here is a superset of C, because if B here is in C and A is in lambda of C, if A is in lambda of C and B is in C, then reasoning as above. So what we have here, is that, what we have shown here is the intersection of something in C and something in lambda of C is in lambda of C, because lambda of C is part of this here. So always when you intersect something in C with lambda of C, you end up with being lambda of C. And here again, so A is in lambda of C, that's in lambda of C. B is in C, then you end up being in lambda of C. That means that this set here is a superset of C. Again, as above, what I have to still argue, I can show that this is a Dynkin system. BA is a Dynkin system, which means that it's not only superset of C, but also superset of lambda of C. And then I'm done, because the BA is a superset of lambda of C, which means that if you take A in lambda of C, B in lambda of C, you end up being in lambda of C, which means that lambda of C is intersection stable, which is exactly what I have to show. So that's the kind of reasoning. So what I'm still missing is the proof of DB is a Dynkin system and BA is a Dynkin system. And here I would just like to mention one thing, maybe the basic thing here. So why should DB be a Dynkin system? So what would I have to show here? First of all, omega is in DB. That's clear, because omega intersect with B, that's B, that's in C, and C is in lambda of C. Okay, that was easy. So if it's a Dynkin system, it has to be set difference stable for subsets. So if I have A, subset of C. What do I need? So A is in dB, C is in dB, then the set difference is also in dB. So both are in dB. And then let's look at the intersection and the set difference. So C without A. So when is C without A in dB? C without A in dB is the case if and only if C without A intersect with B is in lambda of C. So that's C without A. So C without A. I can just write it differently. C intersect with B. Without A intersect with B, like this here. C intersect with B is in lambda of C. A intersect with B is also in lambda of C because A is in dB. And where I am now, I have to show this here. So I have to show, okay, that's just a reformulation. I had to show that this here is in lambda of C. Yes, and I have this here should be in lambda of C. So C intersect with B without A intersect with B. That's in lambda of C. That's in lambda of C. They have the same property that A intersect B is subset of C intersect B. Lambda of C is a Dynkin system, so this here is again in lambda of C. And that's so because lambda of C is a Dynkin system, I have shown that dB has the property required for a Dynkin system. And the argument is similar for the other property of Dynkin systems, which is this increasing set here, and the union is in D also. And here below, the argument is also similar. So that was this theorem that we have. And now we again have to deal with some topology. In the last video, we already recalled some things about topologies. So open sets, metrics define topologies. Closed sets are complements of open sets, but we did not cover yet compact sets, and we will also need compact sets here. So what is a compact set? And usually you learn this also in your first semester or something, or second semester, but let me just recall this. It's in the appendix of the manuscript also. Again, I only argue here with metric spaces because that's the simplest. A space is compact, and also note that we are not dealing with the case that omega is just a subset of Rd or Rn. It's just a general metric space, such that I don't really have what you sometimes also learn in your first year, that a set is compact if and only if it's closed and bounded. I have something similar, as you will see, but I'm more general here. So when is a set compact? It's compact if every open cover has a finite partial cover. So what's an open cover? It's a cover which means K is a subset of some union of open sets. Then there is also a J, which is a finite subset of I, of this index set here, which is also a cover. So let's just see a counterexample. So you might know that the, well, maybe semi-open interval is not compact. Not compact. So why is that? I could write 0, 1 is the union n from 1 to infinity of the set 1 over n to 1. That's true, I guess. Every member of this here is a member here and vice versa. Oh, wait. I have to have an open cover. So it's maybe not so good to have 1 here. Let's do 2 here. So this here, the set of all these sets here, these are the OIs, that's an infinite cover of the set here. And is there a finite partial cover? Which means, can I write 0, 1 as a union here which ends somewhere at a big N or something? Of course not. So that's not the case. Which means that this set here is not compact because it doesn't fulfill the requirement here. Okay, that's why when you exclude 0 here, it's not compact. If you include 0 here, it's compact because then this here does not hold. It also does not hold if I make square brackets here. And then it's compact. You can think about by that yourself why that's compact then. So that's the definition. Okay, I also need relatively compact. And I have also not explained to you what K bar is, but I could have done this last time. K bar is the intersection of all C bigger than K closed C. So it's the intersection of all closed supersets of K. So that's the closure of K. Relatively compact if the closure of K is compact. We also need something relatively sequentially compact if every sequence has a convergent subsequence. And I have to note that the convergent subsequence, the limit point doesn't have to be in K, just in omega. And the fourth thing is totally bounded. A set is totally bounded. For example here, this set here is totally bounded because for all epsilon, which is a radius, for all epsilon here, you can find finitely many points, which are the centers of balls, such that you can cover K with these finite number of balls of size of radius epsilon around the omega ends. Well, of course, you can do this here. If, for example, epsilon is 0.1, I can use a center as 0, 0.1, 0.2, 0.3, and so on. And with these centers, I will cover the set here, and I just need 10 or 11 balls. In the manuscript, you can also read a bit more about connections of compact and other sets. For example, every compact set is closed. You can read there. And the reason is, if you have a compact set, you can show that the complement is open by using the first property here of compactness. So every compact set is closed. And what I will need here frequently is the following. And that basically generalizes the thing that you know from R or RD, that a set is compact if and only if it's closed and totally bounded. And that's as follows. I have 4 properties. Case relatively compact, relatively sequentially compact, totally bounded, and here a 4th thing, which really you should understand as connected to the definition of compact. So here in compact you had a finite cover, but here I have something else. I have the FIs are closed sets, and I know that their intersection is the empty set. And when that's the case, then there's a finite J such that the intersection of the FIs I and J is already the empty set. So this empty set here can already be generated by using a finite index set here. These 4 properties, and they are essentially the same if omega is nice enough, which means it's separable and complete. We had this last time. So in general, only 1 and 2 are the same, relatively compact, and this here is the same. But if O is separable, then you can also come from relatively compact to relatively sequentially compact. Wait a moment, no. This direction is always the case. Compact, from compact it follows sequentially compact. But if it's separable, you also come from relatively sequentially compact to compact. Okay, and that's the first thing. And totally bounded means relatively sequentially compact, which if separable means also relatively complex. So in a complete inseparable space, you have that totally bounded is the same as relatively compact. So omega complete on separable, you have K totally bounded if and only if K bar is compact. And one thing which also holds, because K is totally bounded if and only if K bar is totally bounded. Because having the closure of a set means that, well, you just need to increase the radii of the balls that you need for total boundedness here by a very small bit. That means K is totally bounded if and only if K bar is totally bounded. So a set K bar is compact if and only if it's totally bounded. And of course K bar is closed because it's closed as the closure of K. Which then means K is compact if and only, if K equals K bar, so it's closed, and K is totally bounded. So that's the generalization of the thing that you know about subsets of RD. So let's come back to the things that we need for measure theory. They're not only compact sets, because we have set systems, now we have compact systems, which are compact set systems. They will be important for constructing measures later on. K is a set system. And I have that the system is a compact system. And that's now similar as we had here in the second property here. It's a compact system if whenever I have the countable intersection of the Kn's, which is the empty set, then I already find finitely many which also have intersection empty. Then if that's the property, then K is called a compact system. You might guess it, an example of a compact system is the set of compact sets. Okay. K is the set of compact subsets of some set omega. First of all, it's intersection stable. I haven't really explained this why, but I have explained. Compact means closed. And what's also true, and I think that's either in the manuscript or an exercise, the intersection of a closed set and a compact set is compact. So closed intersected with compact is compact. And so therefore the intersection of a compact set, which is also closed by this here, and compact is also compact. So the set of compact systems, so the set of compact sets, the set system of compact sets is intersection stable. That's also pretty clear from the definition actually. That's a compact system, which means, let's assume you have a set of compact sets, the intersection of which is the empty set. Then I have to see that there's already a finite big N, such that the intersection of the first N is already also the empty set. Why is that the case? So I can write this here as K1 intersected with Kn. So Ln is K1 intersected with Kn. That's a subset of K1. So all Ln's are subsets of K1. And they are compact, therefore also closed, which means take the Ln's as the Fi's here. So here I had the Fi's are closed, and the intersection of them is the empty set. And if this thing here is compact, which is now K1, then I have that the intersection of finitely many is already also the empty set. So I can find a capital N such that the intersection of the Ln's is already the empty set, but the intersection of the first capital N Ln's is just this here. And therefore I have this property, which is exactly what I need for the system to be compact. So, not surprising, the set of compact sets is a compact system. And I need one more property. Later on sometime, I will not go completely through the proof because it's just very many indices. If I have a compact system, and I take the system of all finite unions of elements of the compact system, then I again have a compact system. So if that's a compact system, K union is also a compact system. Yeah. So let me just draw why that could be the case. So what do I need for K to be a compact system? I need to have here some intersection, then there's also a finite N such that the intersection is also empty. Now I have here the set system of these unions here. And I would start with, this here, and here I have the unions is equal to empty set. But let me mention I can also turn this around here. So I can also say it's a complex system if and only if this here is not the empty set, so it's unequal empty set for all n, then this intersection here is also not empty. So that's the same thing to say that if this here is the empty set, then there is something like here also the empty set. It's the same to say for all n, it's true that if this here is not the empty set for all n, then this here is also not the empty set. Well, so that's not the empty set, but now I don't have the ki's here, I have the li's, which are just finite unions of the k's here. I have this here is not the empty set for all n, and I have to show that the countable intersection is also not the empty set. Well, and the reason is, yeah, so this here should not be the empty set for all n. And what are the ln's? Well, the ln's are some unions. So this here is an ln. That's a union of the kjn's. So that's k1n, k2n, km, n, yeah. So that's ln, and the intersection of all these is not the empty set. So I have here ln plus 1. So also some k, some other k, some other k. The intersection of this here, and so on, is not the empty set. And how can that be the case? Well, I have some k's here where the intersection is not the empty set. Otherwise, it just doesn't work. And basically what I'm doing here in the proof, and with a bit more text in the manuscript, is to make this more rigorous. So if these intersections are not the empty set, I also can find some k's such that they're not the intersection is not the empty set. Basically what I show here is via induction. And let me just read this induction here for the small k equals to 0. For every n, there are sets k1 to kn with kn a subset of ln, such that the kn is, well, maybe this one here, such that for k we have that the intersection of these here, well, and below them you can use the whole unions again, or maybe not. For k equals 0, then this here is gone. We have k1 to kn is not the empty set. Well, and if I have this, then I can just use the property of k being a compact system, which then means, since I have that for all n, I have that the first finitely many things are not the empty set, that then I also have that the intersection of all the kn's are not the empty set, but of course these here are subsets of the intersection of the ln's, and then I'm done in showing that k union here is also a compact system. Yeah, so that's a pretty special lemma we need here. We need that later, basically I think in the last section of this manuscript, but then we already have it. Okay, very good. Then see you next time. Then we have finished by today these set systems, and next time we will define functions on set systems. See you then.